So the next speaker is Andres Gurpide, who is going to talk about the discovery of a recurrent spectral evolutionary cycle in a couple of ULXs. Oh, good.
All right. So thanks, Marianne, for highlighting that we don't know anything about ULXs. That's not far from the truth. My name is Andres Gurpide. I'm a third-year PhD student at the Institute for Astrophysics and Planetology in Toulouse, France. And I'm working on X-ray observations and optical observations of ULXs, trying to understand the Super Eddington regime. And I think what I want to talk about today is fits very nicely with the theme of this conference, because we think we have discovered some sort of evolutionary cycle that might be reminiscent of this Q-shaped diagram that we have discussed for so long. So I would like to start this talk by showing you these beautiful images that Marianne has already touched on. And I think this is the telltale that these systems really are exhibiting some enormous power beyond what we see in our own galaxy. And I would like to draw the attention of the audience to the recent addition to this set of beautiful images, where we have discovered a bubble extending 400 parsecs. And as I said, I think there is nothing in our galaxy that resembles these things except for the microquasar SS433. And this is a fascinating object that we have reasons to believe that it's accreting at Super Eddington rates. And it has two steady jets that precess and are thought to have distorted the supernova remnant that gave birth to the object, creating this beautiful seashell nebula. But SS433 is very dim in X-ray. So how do we kind of link these two objects together? And the answer may be Super Eddington accretion. So first of all, I would like to apologize if my cartoon doesn't do any justice to the numerical simulations of Super Eddington accretion flows. But just to set some basic ideas. So when the mass accretion rate exceeds the limit set by the classical Eddington limit, the disk will become radiation supported, will puff up, and then you will have a radiatively driven outflow launching from the surface of the disk. And this outflow leaves the disk due to angular momentum conservation. It will create a funnel or cone structure where an observer that views the system from rather a phase-on view will see a ULX spectrum, so 10 to the 40, 10 to the 39 per second. And as you increase the inclination, more of the wind will be in your line of sight. This wind will downscatter the emission from the inner parts of the accretion disk, and it will soften the spectrum, so you will see a soft ULX. And then the idea is that at very extreme inclinations, or perhaps high accretion rates, you only see the wind photosphere and you see a super soft ULX. The idea also is that when the mass accretion rate increases, the outflow rate increases. So these sources may change, or a source may change into these states, as I will show later. And SS433 then fits nicely in this picture because the inclination is almost 80 degrees. So because we don't see the inner parts of the accretion disk, we see a source that is very dim. Now, when we thought we had an idea of how these things work, someone in this room discovered pulsations in one of these systems, turning the entire field upside down and showing that, again, we don't know anything about the Super Eddington regime. And of course, the question now is, do these pictures still hold for a neutron star, or do we have to rethink everything I just explained? And there are very simplistic, kind of opposing views. So some people argue that ULXs are lowly magnetized. So because the magnetospheric radius depends on the accretion rate, the disk is truncated very close to the neutron star. So you still form this Super Eddington accretion disk and you still have these outflows. But then some other people argue that no, you need high magnetic fields to surpass the Eddington limit. And in this case, because the disk will be truncated very far, you won't have any outflows. And now with this said, I will talk about my work. And early this year, I was naive enough that I thought I could distinguish neutron stars from black hole ULXs through X-ray spectroscopy, in particular looking at their spectral transitions. And one of the things I was looking at also was trying to find ULXs that varied in a similar manner. And here I show two ULXs that vary exactly in the similar way. And I highlight some spectral states that you see. So this is a hardness luminosity diagram. This is a spectral decomposition from some states. And the sources really transit through these states I just outlined. So we have the hard ultraluminous, soft ultraluminous, and super soft. But from these data, I could not really tell whether how long the sources spend in this state. Is there any connection between these states, how these things vary? So then I looked at the Swift archival data, and this is the main result of this talk. And I could really see, so here you have the Swift light curve and the hardness intensity diagram. And you can really see that we have clearly two distinct modes of variability or accretion states. So we have this, this blue part of the light curve, we can identify as the hard ultraluminous state. And you can see that it's a state that doesn't vary at all. We had monitoring for 240 days, very stable. And quite remarkably, we have this other state where the source softens and transits back and forth very rapidly, as you can see from the light curves, sometimes within a day, between these two states. Now, the nice thing is that because I already told you that these two sources are basically the same thing, I could analyze some data I hadn't taken into account in the previous paper and show that, again, we have the same thing. So these Chandra observations were taken within a few days. So I could see again that I have these transitions, and here you have the Swift equivalent count rates. And then something very important as well is that we could find or see that the source transits from the hard ultraluminous to the soft ultraluminous, and then it goes back from the soft ultraluminous to the hard ultraluminous. So putting all these together, you can explain this cycle, but the source transiting from here goes to here, then it will transit back and forth, and then it will go back to the hard ultraluminous. So as opposed to Xray binaries, we don't find evidence for hysteresis, for instance. And the key takeaway of this talk is that with these cycles now, perhaps we can start to build a self-consistent picture of the supraintern accretion regime, much as we do with the Q-shaped diagram. Now, another thing we wanted to look at is whether these transitions were associated to any periodicity. So for this, we conducted Lomskargel periodograms. So these are like Fourier transforms for unevenly sampled data. And we found this peak that, depending on your considerations, could or not be significant. So of course, depends on what you assume as your null hypothesis. So based on all this evidence, now I will present some ideas on how we can interpret this cycle. These are ideas that need to be tested, of course, but so basically, we have our hard intermediate state or hard ultraluminous. And the idea is that we look at the source, rather low inclination angle. And because the mass accretion rate is low, we expect this funnel to be rather open. So because the wind is not entering the line of sight, we see a state that is very stable, no much variability. But then as the mass accretion rate increases, because the funnel is expected to narrow as more wind is pushed from the disk, then this will increase the amount of downscattering. You will have more of the wind on the line of sight. So we can understand this softening as an increase of the mass accretion rate. And now, because it is expected that the wind will be closer to our line of sight, now the wind might intermittently enter off line of sight and create this rapid variability. Of course, this needs, for this, we need to study in detail the wind properties to assess these claims, but as I said, some ideas. And then, of course, I told you that perhaps these changes are periodic. So in this case, it has been invoked that this accretion flow can precess. So again, similar idea in the hard ultraluminous, mass accretion rate is low. Your funnel might precess, but because you're always looking into the inner regions of the accretion flow, you don't expect much variability. But when the mass accretion rate increases, the funnel will narrow. Now the wind is close to your line of sight, and when this thing precesses, you expect very strong changes as the wind comes in and out of the line of sight. So again, this thing. Another great thing about this is that now you can go back to the archival data, see when your source was observed in a particular state, and retrieve all the data you can. And this is more or less what I did. So I retrieved all the XM Newton data for all the Nussler data and HST for a particular state. And we try to use, in ULXs, we don't have many self-consistent models. So I try to use a model that is basically a self-irradiated funnel. So
2 minutes.
Okay. For those of you who work on Xray binaries, it's like the disk irradiated model, but for the superhélice accretion. And the key takeaway is that we could model these two sources as having a rather low inclination angle, wide open funnel, and then perhaps explain the brightness and softness of Holmberg 2x1 as having a higher accretion rate or ejection rate. All right, so I reached my conclusions. I hope I have convinced you that now that we know how these sources evolve, we know this pattern repeats, so perhaps it's time to think of how to explain these variations in a similar way we do as for the Q-shaped diagram. And I would like to bring up again this diagram Rob showed to say that for ULXs, we don't have quality data, we don't have good models, so we're really touching the surface of this phenomenological behavior. And last thing, so if I may have 30 seconds. So we recently submitted this paper on a new discovery of a bubble around NGC 1313X1. And you can see the normal size of these things. And another thing that can be looked for from this image directly is that you can see that the line ratios around the bubble are clearly different from the gas that is being ionized by stars. And these already tell us that this gas here is being shocked. And I will conclude by saying that we also find some evidence for high velocity shift close to the compact object. So we think this really points to a scenario where this object is carving the ISM through winds and jets. So I'll be happy to take some questions now.
Thank you, Andres. Do we have any question? I don't see any on the Zoom, maybe in the room.
Yes, we have a question.
Okay.
People did mention the Sakura Sunyaev alpha. What sort of range would you get?
For what, sorry?
For the alpha SS. The alpha SS. What alpha SS will you get?
What, sorry?
The alpha SS, the Sakura Sunyaev viscosity parameter. The alpha.
Ah, the alpha parameter. In the spectral modeling. So that's not a model of that's not a parameter of the model as far as I'm aware. I mean, you're talking about the viscosity parameter, right? Yeah, okay. I don't think that's a parameter of the model, and to be honest, I don't know the technical details of what assumption of the viscosity is done in this particular model.
We have a question on the Slack. Maybe you want to ask it, or I can do it for you, Hemant. So I will say.
Here,
sorry.
Here is Agata. One more
there
question.
was. Sorry, Agata. There was a question on the Slack before. What could be the possible reason for ULX spectra cutting off at relatively low energy of about 10 keV? Compared to X-ray pulsars, which cut off at higher energies?
Yeah, I don't think we have a clear understanding of that. One reason to explain this cutoff is that you have downscattering in the wind, and you are basically missing most of the high energy radiation.
Okay, thank you. Yeah, sorry, Agata, you can go ahead.
So first, the comment to the previous question. For the time being, in X-ray domain, we have no model which can constrain alpha parameter. So if we fit the disk model, it is only a spectrum. So you cannot constrain any viscosity. So viscosity is still something in the black box. From the point of fitting, of course. And so my comment is only that recently my student also published state transition in one ULX, Circinus ULX5, and the time scale was 210 days, so 7 months.
Okay.
So I will be happy to maybe talk and
sure. Sounds
compare.
Good.
Okay, so let's thank Andres again.